Hello, this is Kyung-Seok Jang, and in this video, I'd like to introduce our recent work, Efficient Low-Rank Matrix Estimation, Experimental Design, and Armset-Dependent Low-Rank Bandits. This is a joint work with Chi-Cheng Zhang and Kwang-Sung Jang. To begin with, I'd like to introduce the formal problem setup of the low-rank bandits. So at every time step t, the learner chooses an arm AT from the arm set curly A and receives the reward YT, which is basically the inner product between the chosen action and the unknown matrix theta star with a known upper bound of the rank at most R plus some perturbation eta t. And the main objective of this problem is minimizing the pseudo regret. This field has been receiving a lot of attention recently, but many of them only deal with specific arm sets, which means that many of the works lacks generality, and this is one problem. And the other problem is the estimation perspective. Many of the works relied on the low-rank estimation literature, traditionally used nuclear non-regularized least square or nuc-RLS. But these studies are mainly for offline setting, where data is given and the learner just need to estimate. In the setting where the learner collects the data, experimental designs are also very important, but because the most literatures relied on low-rank estimation, many of the works simply ignored this experimental design perspective, and there were not enough discussions on this experimental design. So this is our fundamental question. So can we design estimation algorithm with experimental design that can outperform the classical nuc-RLS and work in general environment? The answer is yes. We proposed a novel and computationally efficient low-rank estimation method called low-pop-art, whose estimation error is not worse and can order-wise better than the classical nuc-RLS. Inspired by this new estimation method, we proposed a computationally tractable designable experiment object BQ-Pi for low-pop-art. Based on these two observations, we also designed two computationally efficient and arm-set geometry adaptive algorithms using low-pop-art called LPA-ETC and LPA-ESTR. As I mentioned, low-pop-art is our new low-rank estimation method, and this is the skeleton of our algorithm. For each sample measurement AI and its observation YI, the algorithm computes one sample estimator tilde theta I, and using these collection of one sample estimators, the algorithm computes the matrix Catoni estimator called theta 1. And then lastly, the algorithm learns singular value decomposition on this Catoni estimator and zeroing out all the singular values which are under the threshold. This is the pseudocode, and throughout the theoretical analysis, we found out that the following quantity, BQ-Pi, determines the variance of the singular values of one sample estimator, tilde theta I. And this observation leads one natural experimental design, which is simply minimizing this quantity BQ-Pi. Turns out this is a convex optimization problem, which is easy to implement. And throughout our theoretical analysis, it turns out that our low-pop-art is always better than the traditional nuc-RLS approach, and in many cases, low-pop-art is order-wise better than the traditional ones. And these two observations lead new algorithms, LPA-ETC and LPA-ESTR, by replacing the existing exploration phase with our low-pop-art-based method. In this approach shows significantly better performance. Here, as you can see, the first algorithm is LPA-ETC, which is replacing the exploration phase of the explored and commit by low-pop-art. This algorithm works with fewer and lenient assumptions, especially no assumptions on lambda mean of the theta star. The second algorithm is LPA-ESTR, which is replacing exploration phase by low-pop-art. And this algorithm shows strictly better performance compared to state-of-the-art algorithms. We also showed the superiority of low-pop-art algorithm by experiments. The first experiment is measuring the estimation of error of the low pop art. And after some analysis, we found out that our experimental design and estimation error generally outperforms the traditional experimental design and estimation error. We also checked the bandit experiments, and in any situations, low pop art based algorithms work better than state-of-the-art algorithms. Thank you for listening, and I hope to see you on the poster session.